Hi, in this video we will introduce the notion of orthogonal complement for subspaces, and then we will see in some examples in R2 and R3 how this works. Well, let me start with the definition. So orthogonal complement of a subspace, we're assuming that there's a subspace, so let W be a subspace of Rn. And then we define the orthogonal complement. So the orthogonal complement of Rn, of W, sorry, which we have a notation for that. We denote it by W perp is a set defined by, so W perp, so W was the original subspace, and now we have W perp. This is a subspace. It is a set of all vectors in Rn such that, well, V is orthogonal to all vectors in the subspace W. So find vectors which are orthogonal to all the vectors of the subspace W, put them together, that will be a set which is W perp. Well, we already know a good way of writing this being orthogonal, a vector being orthogonal, so we can rewrite this set as take all the vectors in Rn such that V is dot W is 0 for all vectors W in the subspace W. Well, you may say that, is there always such a thing? So let me write remark W perp is always non-empty. Means that there is always something there. There is always a vector which is perpendicular to all the vectors of the given subspace. And indeed, zero vector is always in W perp. Why is that so? Because zero vector dot any vector in W, or even in general in Rn, this is going to be 0. So for all vectors W in subspace W. So that means that zero vector is in W perp. So that's at least we know that always zero vector is there. Well, in R2, R3, this can be actually seen what is happening for the perp geometrically. Okay, let's do some examples. For example, look at this guy. The W here is or xy's such that 3x minus 2y is equal to 0. We know that this is the line through the origin, with normal vector x, the normal vector, you know that you pick the coefficients of x and y from the general form. In this case, it is 3 and 2. So now you have a vector, a line in R2, and you're looking, and you know that there is a vector, normal vector n there. Okay. Oh, it is 3 and negative 2. Sorry, 3 and negative 2. So this will be 3, negative 2. Now, you're looking for all the vectors which are perpendicular to this line. Well, if you put all those together, you will notice that this will form a line which passes through the origin. Why? Because the origin is always in W perp, the zero vector, and this time the line is going to be parallel to 3 and negative 2. So W perp is going to be the line through the origin with direction vector, with the direction vector 3 and negative 2. You see, now you can write different equations for that. For example, we know that this will be all xy's such that xy is equal to t times 3 negative 2. Or you can write the general form. You see that such a line has the normal vector 2, 3. So then this will be all xy's such that 2x plus 3y equals to 0. Where did I get 2, 3? Remember, if you have a vector and you want to find another vector in R2 which is orthogonal to that, you switch the entries, multiply one of the entries by negative sign. So in this case, 2 is up there and 3, and I multiplied the first component by negative sign. That's nice. At least geometrically we can see what is W perp here. Let's do this one. So here W is, well, look at the equation. This is equation of a plane. So this is the plane through the origin again. Okay. And with a normal vector n. Remember, if you have the general form equation for a plane, the coefficients of x, y, z form a normal vector for that plane. Very nice. Now that we have a normal vector, we know, well, this is, now we have a plane in R3, and we have a normal vector for that, which is, I don't know, 1 and negative 1, negative 1. Then all the vectors which are orthogonal to this plane, these are going to form a line. A line which is this time parallel to that vector 1, negative 1, negative 1. So W perp is going to be the line through the origin, because it contains the zero vector, a parallel to vector 1 and negative 1 and negative 1. And we can write equation for this, yes. So this will form like x, y, z, such that, well, x, y, z are multiple of, well, 0 plus t times 1 negative vector form of this line. Or we can make the parametric form also. Yes, so it will be x is equal to t, y is equal to negative t, and z is equal to negative t. That's another example. Well, also we can have the third one, the third case where, well, the equation this time is parametric equation of a line. So this is the line through the origin with and parallel to the vector you see, the coefficients of t in the parametric equations, 2, negative 1, 3. Okay, so if you, this time we are in R3, and we have W as a line, and we have a direction vector like D. Now, all the vectors which are perpendicular to this line, this will form a plane here. So if we go like that, and let's say from the origin, and will be perpendicular to that. And the funny thing is that this D here can be considered as a normal vector for that W perp or that plane. So W perp is the plane through the origin with a normal vector 2, -1, 3. Yeah, well, we can write it as x, y, z, such that 2x, the general form of such an equation, such a plane, 2x minus y plus 3z equals to 0. So these were basic examples. In the next videos, we will learn how to find at least what are the properties and how to find a basis for the orthogonal complement of a subspace.